So far in our discussion of optics, we've talked a little bit about reflection, a little bit about refraction in their simplest cases, which is when light is interacting with flat surfaces only. What we're going to get into next is lenses and mirrors that are curved. So these are optical instruments that, their sole purpose, they were designed to focus light in a certain way. And we're going to talk about how we can predict in which way they'll focus light. So when you have light striking a curved surface, it's a little bit more complicated than flat surfaces, but um, really it's all the same principles that we're dealing with. So any given light ray strikes on an infinitely small portion of the lens or the mirror that you're working with. And that small portion, just by itself, if we take one little section of the lens or the mirror, it's pretty flat. So based on that, we can still think about a normal line, so some line that's perpendicular to a tangent plane, a line that would be tangent to your surface, like you see in this picture here. So we have one ray that we're looking at. It comes in, hits this curved surface, and at that one single point, we can try to treat it like a flat surface, and it would bounce off and reflect, or it would pass through, um, bend a little bit, and be refracted. So now we're going to be talking about normal lines being perpendicular to a tangent line. So we're going to cover four basic kinds of optical instruments. So we'll talk about what was the order here? Whoa, my caps lock. Alright, I thought I fixed it. Concave mirrors, which means they bend inward. After concave mirrors, we'll talk about convex mirrors. Those are the ones that bend outward. And these are the two that we're going to hit in this video. The rest will come at a later time. So the last two will be concave lenses. And last one, convex lenses. So lenses that bend inward and lenses that bend outward. So if you have trouble remembering the difference between concave and convex, just remember the word cave is literally in the word concave, and concave mirrors bend in like a cave. So the only thing left for convex would to be they bulge outward. You might think X, like external, they bend out. Alright, so in general they have a few characteristics that are the same. So a lot of the vocabulary that we're working with is going to have the same meaning for all the different instruments. So before we look at each one individually, let's start out looking at the things that they have in common. So we have a little diagram here of a concave mirror. So the shiny surface, you could tell, would be where all the light rays are reflecting. So we're going to get into some diagrams. This set of notes happens to call them ray tracing. You might run into a few different names, but all we're doing is tracing out the way that a light ray would behave if it came into contact with the mirror. So this one shows how a certain ray, well, two certain rays would bounce off of it. And we're just going to take this, like I said, as an example, but the same principles and vocabulary are going to apply to the other objects that we talk about as well. So on our first blank here, it's a normal line, and it's typically going to run right through the center of the mirror or the lens that you're working with. In the diagram, it's the horizontal gray line right here. So that one we're going to call our principal axis. So that's the one that runs right through the center. The next thing, represented by the letter V in the diagram, is the point where the principal axis intersects with the mirror of the lens. So right here at point V, we're going to call that our vertex. So principal axis runs into the mirror right here at the vertex. The only mirrors that we need to worry ourselves with for right now are called spherical mirrors, and it's just like it sounds. If it continued the whole way around, it would form a sphere. So we just chop off some little piece, and that's the mirror we're working with. So all of our spherical mirrors are going to have, you can see represented by C here, and that is going to be our center of curvature. So if we continued the whole sphere the whole way around, that C would be right in the middle. So if we drew a line from C to any point on the sphere, all we're doing is taking, or sorry, the mirror, all we're doing is taking a radius. So we're going to call the line R in your diagram the radius of curvature. So we said the whole purpose of using curved mirrors and lenses was to kind of focus these light rays into a certain point. So if you look at this diagram, we have two different light rays, one that comes in here and gets reflected off. You can see very faintly the tangent line drawn there. So we have tangent, our radius of curvature kind of acts as the normal here. So it bounces off, the angle of incidence inside there is equal to the angle of reflection as it bounces back through. You can see another light ray here that kind of comes in at an angle and then bounces off parallel to the principal axis. So this point F, that's the point where everything gets focused. So the point F is called the focal point, where all the light rays get reflected to. Alright, so just to clarify a little bit, if it comes in parallel, it goes through the focal point after reflecting. If it goes through the focal point before it hits the mirror, then it gets reflected parallel. So conversely, a ray of light that passes through the focal point gets reflected parallel to the principal axis. So one last little variable to define here. You can see the little f right in there. So the distance between the vertex V and the focal point F is called the focal length. So focal length literally is the distance between the vertex and the focal point. For any spherical mirror, the focal length is going to be half your radius of curvature. So F is always R divided by 2.